Hi, everyone, and welcome back. It's Kira Garfolo with Greenville Tech's Math 120. Today, we're going to talk about Chapter 5 in the textbook. So today, we're going to mainly focus on Section 5.1, although that's really the only section that we fully cover in Chapter 5. It's definitely worth a read if it's of interest to you, and we're going to pick up some other important topics along the way that are not included in 5.1, and I'll be sure to point those out. As far as anything for homework, tests, all of the like, anything that you need to understand is going to be in 5.1 as well as in this slide set. Okay, so anything that's outside of 5.1 is something that we will cover explicitly. So with Chapter 5, we've dived into Unit 2. Unit 2 is all about probability. So we're going to talk about the basics of probability today. Then we'll get into some kind of basics of probability distributions for both discrete and continuous cases. We'll talk about some special distributions, mainly the binomial, the uniform, and the normal distribution. And then we will talk about sampling distributions to wrap up Unit 2 and Chapter 8 before our next test. Just a word of caution, not to scare you or make you think, oh, this is going to be bad. It's not. But most students find Unit 2 to be the harder of the 3 units, especially if you found Unit 1 to be particularly easy, since it was mostly a review of stuff you'd seen before. If that was you, make sure that you are keeping up with Unit 2, because it's probably going to challenge you a little bit more than Unit 1. Okay. So first things first, I want you to think about what is probability. So if I had just asked you standing in a classroom or standing in the hallway, hey, what do you think probability is? How would you define it? Well, mathematically speaking, we say that probability is the likelihood of a random process resulting in a specific outcome. Okay, that's a very technical definition of it. You can think about likelihood as a chance. Okay, so the probability, kind of reduced into simpler terms, is just the chance that a certain outcome is going to occur while the process is on. Okay, so the process still has to be random. We don't know what it's going to be, but if you think about tossing a coin or rolling a die, something like that, where you don't know the outcome, you can talk about the probability of certain outcomes. So what's the chance you're going to get tails on an even or on a fair coin? Okay, something like that. That is going to be probability. In practice, we can also think about it as the proportion that a certain outcome occurs in the long run. Okay, so maybe you don't know for sure that you're dealing with a fair coin, but if you flip a coin over and over and over and over again, you can get a good idea of what the probability of tails will be by simply looking at that relative frequency of tails overall. Okay, so for example, if I flipped a coin 10,000 times and observed somewhere around 5,000 tails, you would assume that it's about 50-50, a 50% or 0.5 probability that that coin will come up to be tails. And that leads us into the concept of the law of large numbers. So the law of large numbers says that as n, or as our number of trials, or as our number of experimental trials continues, as it grows, the proportion in which a particular outcome is observed approaches the probability of that outcome occurring. Okay, so that sounds very technical again, but really the concept is fairly simple, and it's something that you've used before without having any idea you were talking about probability. Okay, so I think about tossing a coin. Okay, so if I toss a coin 6 times, okay, if I toss a coin 6 times and I know that it's a fair coin, then sure, I would expect 3 heads, 3 tails. But the reality is, if all of you grabbed a coin right now and tossed it 6 times, most of you wouldn't get 3 and 3, okay? Even if you got 1 and 5, you wouldn't be totally concerned that your coin is unfair. However, if you toss your coin 100 times, you would certainly hope that somewhere around half is heads. If you tossed it 1,000 times or 10,000 times, you would expect, again, it doesn't have to be perfectly half, but as those number of trials grows, you would expect that proportion to approach 50% if you are dealing with an actual fair coin. So if that true probability is 50%, then you would expect, as you flipped it more and more and more and more, that your true proportion, your observed proportion, was approaching that true probability. Okay, and we can demonstrate this in StatCrunch. You're not going to ever be asked to do this in StatCrunch. Okay, this is just an applet for display purposes. But we can go into the experimental applets and we can talk about flipping a coin. Okay. So if I flip a coin one time, I get one tails. I can flip it lots and lots and lots and lots of times. And the more I do this, okay, I'm staying real close to 50% here. Okay. So it's certainly helping me. I'm not terribly far from there. Okay. Now, the law of large numbers, though, let's see, simulation is probably a better choice for us. Coin flipping, this is going to allow us to do it more than once. Okay, so let's do a random coin flipping. So if I flip a coin 5 times, that shows us all of it, okay? It shows the number of heads, or the proportion of heads, is 0.4. Does that mean that our heads or our coin is biased away from heads and towards tails? No, it doesn't. Because 2 out of 5, we can't have a perfect 2.5 out of 5 anyway. It's going to have to go one way or another. Okay, if we do 5 more, our proportion is exactly 0.5. Okay, we do 5 more, we're still hovering around that 0.5. Okay, of course, by chance, I'm getting great answers here, right? If I reset it here and do this, sometimes I get a really good example. Finally, I got a good example here, okay? So this time I tossed it 5 times, and 4 out of those 5 times were heads. Okay, but I know I have told the program that I want a perfectly even likelihood coin. Okay, so I want 0.5 as my probability. Are we concerned yet that our coin is not actually even? No, not yet, because we only tossed it 5 times. It's nothing to worry about. But if I keep doing it more and more and more, so now I've done 1,005 because I just did 1,000, notice that our proportion is getting closer and closer to 0.5. And I can do this over and over and over. And the more I do, the more I should see it hovering really close to 0.5. Okay. And it can go above, it can go below, but it's going to hover right there around 0.5. Again, you're very rarely going to get a perfect 0.5 in experimental data. So again, the law of large numbers just says, hey, as you repeat this over and over and over again, the proportion of that outcome you're interested in should approach that true probability. So let's talk about some foundations of probability more in depth. So last unit, we described an experiment as some sort of design where we had a control group and a treatment group, or at least 2 groups, and we were manipulating that independent variable. That is not really what we're talking about when we say we have a probability experiment, okay? We're talking about something much simpler. For our purposes, a probability experiment is just any repeatable process with an uncertain result. So I toss a single coin. I toss a fair die. Okay, all of those are going to be considered probability experiments. We're going to denote the probability as P, and probability is just the chance that it occurs. Our sample space is going to be S. Okay, it's going to be a capital S. And our sample space is simply a listing of all of our possible outcomes. Okay, so we'll talk about an example here in a minute to talk about sample space. But if I toss a fair coin, my sample space is heads or tails, because it is a listing of all the possible options for that single toss. We can have events, and events are certain desired outcomes or outcomes that we're modeling, okay? I am going to talk about capitalized E and little e here. I am never coming after you for this notation, but you will see it in your textbook and you'll see it in other places, so it's worth a discussion. If we see a capital E, it is most commonly what we call a compound event. Okay, so in a compound event, we have more than one way to reach it. Okay, and I'll talk about that with our example here in a moment. If we see a little e, then that is usually a simple event in which there is one way to get it. Usually your subscript here, this little I, is going to tell you what the outcome is. So we had little e with a subscript of T. Okay, maybe that would be the event that we get tails when we toss our coin. Okay, so let's talk about some examples here. Let's say that I toss a fair die. So remember that when I toss a fair die, what can I get? That is my sample space. Okay, so my sample space is going to be a listing of all my possible outcomes. So it is going to be, I could get a 1, a 2, a 3, a 4, a 5, or a 6. Okay, those are going to be my possible outcomes. I can talk about a simple event. Let's say that it's E4. Okay, this is the event that I roll a 4. Okay, so this is the event I roll a 4. Okay, I can also name a compound event. So let's let it be capital E, be the event you roll an even. Okay, how can we roll an even? Since it's a capital E, we know it's a compound event, so there's more than one way to get it. I roll an even if I roll a 2, a 4, or if I roll a 6. Okay, all of those are going to be even numbers. Okay, so that is that in a nutshell. You guys can even jump forward to probability if you think about it. What is going to be the probability that E4 occurs? Well, how many ways can I roll a 4? If I toss a fair die, how many ways can I get a 4? Well, there's one way to get a 4 out of the 6 total ways. What about the probability that I roll an even? Well, 2, 4, 6 are 3 different ways out of 6 possibilities, which is going to be 0.5. Okay. Now, there's some rules governing probability that stick with kind of all probability in our course and beyond. Okay. The probability of any single event or outcome must be between 0 and 1 inclusive. Okay. If I tell you that something has a probability of 0 happening, 0 means that it is an impossible account or an impossible event. Okay. So if you think about the probability that you roll a fair standard die, so you had that 1, 2, 3, 4, 5, 6, the probability that you roll a 7 is impossible. So it's 0. Okay. The probability that you roll a 1 is going to be a definite outcome. Okay. So it is going to be what we call a certainty. It is going to happen. Okay. So the probability that I roll an even or an odd number, well, that's going to be 1 because it's either going to be even or it's going to be odd. Okay. We also know that the sum of the probability for independent events, for individual outcomes, must be 1. Okay. So again, this is just the summation. Okay. If I add up all of the probabilities for all of my individual outcomes, they have to add up to be 1. So thinking about the tossing the fair die, the probability I get a 1 plus the probability I get a 2 plus the probability of 3 plus the probability of 4 plus the probability of 5 plus the probability of 6 is going to be 1. That's because I have 1, 6 plus 1, 6 plus 1, 6, 6 times to give me a 1. Okay. Also, kind of a semantics thing. Probability only exists while the outcome is uncertain. Okay. It only exists while you're talking about not knowing the outcome. So if I'm looking outside my window and I see that it's rain, I cannot say, oh, there's a 20% chance of rain today because it's already raining. I already know that it is raining. Okay. Now, if I'm saying, oh, there's a 20% chance of rain tomorrow, that's fine because I don't know what it's doing tomorrow. If I say, well, the weatherman said that there was only a 20% chance of rain today and now it's raining. Well, there's nothing wrong with that statement either because it's in past tense. Okay. There was a 20% chance and it happened. Okay. So you cannot look outside at the rain and say, well, now that it's raining, there's a 20% chance. That doesn't make any sense because you already know what happened. And remember, it must be uncertain outcome for you to know for you to put a probability on it. Okay, we can also talk about something called a probability model. You guys have used these and you've not called it a probability model. Okay. Basically, a probability model is going to occur when you list all possible outcomes for the experiment along with their probabilities. Okay. So the probability for our die throw here, we throw a single die. We know that we could list and get a 1, 2, 3, 4, 5, or 6. That was our sample space. And the probability for each of them is equal because it's a fair die of 1/6. That's a probability model. That's a table representing your probability model. Okay. Our textbook gives an example of candies. I don't know if it's M&Ms or something similar, but it says, okay, well, let's say that the probability you select a brown is 0.13, a yellow is 0.14, and so on. This is a probability model over here for the candies, okay? The idea here is that you are listing all possibilities and you're listing their probabilities. Now, I'm not asking you to calculate these probabilities right now. They have given those to us. We just are representing them in a probability model. So how do I interpret a probability? Well, the closer a probability is to 1, the more likely it is to occur. Okay? Again, chances of rain. If the weatherman says that there is a 10% chance of rain tomorrow, you'll probably be fairly comfortable walking out with no umbrella. However, if the weatherman says, hey, there's a 90% chance of rain tomorrow, you're probably going to grab your umbrella, right? So the closer a probability is to 1 or 100%, the more likely it is to occur. So this is a good place for a note. The probability as decimals is fine. You can also convert it into percents. Okay. So a 20% chance is going to be the same as a probability of 0.2 or 0.20 if you want to write it. Okay. Feel comfortable going back and forth between them. Now, just to kind of drive home that concept of the law of large numbers. With repeated trials, we expect that proportion of results to be consistent with the probability. Okay. So over and over and over again, you expect that proportion of observed outcomes to approach the true probability. So we've already talked about the law of large numbers, tossing a fair coin, tossing a fair die. Okay. A lot of this is how gambling red flags work, right? If the pit boss is watching you and you are getting lots and lots and lots of very lucky tosses or very lucky slot machine pulls, they're going to start to get concerned. If you win 2 jackpots in a row, they might be concerned, but they don't really have a leg to stand on to accuse you of anything yet without other evidence. However, if you pull it 1,000 times and they notice that in 1,000 times it has paid out, it's only supposed to pay out 2% of the time, but out of 1,000 times it pays out, 110. Well, that is now an 11% chance versus a 2% chance. And after that many runs, there's some pretty solid evidence, right? So if you just do it a few times, it's not enough to convince you. But if it is showing kind of that pattern over the long run, you're going to get concerned. Okay, that's all that law of large numbers is telling you. So what makes an event unusual? Okay, so this is kind of our first case of using the word sufficiently in a statistics course, but statisticians love the word sufficiently. Okay, so if the probability of an event is sufficiently small, we say that that event is unusual. So if its probability is small enough, it's unusual. So what makes it small enough? Well, typically we are going to use the cutoff of 5% or 0.05. Okay, so 0.05 or 5%. Anything less than that is going to have an unusual outcome. Okay. Now, this is somewhat of a flexible rule of thumb. It's not really set in stone, okay? Different cutoffs can be determined based on different situations. So if we had 5%, let's say that you were all in my class and I gave you all a pill, okay? And I said, hey, this pill is going to do great things. You are going to all be able to think super clearly. You can think about it like a limitless pill, okay? You're going to ace your test. You're going to do whatever. Cool, that sounds great. Now, if I say, don't worry, about 5% of you are going to get a dry mouth, but I've got some water bottles right here. You'll be okay. You wouldn't be too concerned, right? However, now let's say same pill, but I say, don't worry, about 5% of you are going to die within 30 minutes of taking this pill. Now you suddenly think 5%, that's a pretty high chance, right? So in cases where there are grave consequences, maybe it's life or death, maybe it's something very expensive, maybe it's something, if you're talking about a diagnostic test where you don't want to miss something bad or you don't want to tell somebody they have something that they don't, in that case, you want to lower that cutoff. And we'll see that throughout our course, especially when we get into inferential statistics, where we are going to cut it off slightly differently at times. Okay, so there are a few different types of probability that we are going to consider. Okay, we're going to talk about empirical probability, we're going to talk about classical probability, and then we're going to talk about a third kind called subjective probability. So empirical probability is going to look at observed results. Okay, so you're going to be looking at real data. Okay, so real data, or you could be talking about simulated data because we're going to treat that like real data. Okay, but in this case, you are talking about actual data. Okay, so let's say that you tossed a coin 100 times. So let's say, hopefully I'm not overwriting anything here. You toss a coin 100 times. Okay, and see that there are 47 tails. This would tell you that your empirical probability of tails is just 47 out of 100. Okay, you guys have done this before. You just called it relative frequency. Okay, so you're going to see how many times it occurred, and you're going to divide it by the total number of trials given. Okay, very nice. I did very much override it. Okay, so again, remember that this is just an estimate of what is actually going to be expected to happen in the long run. Okay, it is probably not going to be perfect. Like we just talked about, if we tossed a coin 100 times and we saw 47 tails, then our probability of tails based on the information we have is 0.47. Okay, that is not necessarily perfect, right? If it was a fair coin, we would know that the theoretical probability, which we're going to rename here in a second, is 50%, not 47%. That is okay. If I sent all of you to do 100 coin tosses, most of you wouldn't get the same exact answer as each other. Okay, that is fine. Variation is to be expected. However, the law of large numbers tells us that as we do it more and more and more and more, we might not all be perfect, but we should all approach the same proportion. Okay, so we shouldn't be getting all over the place after 100 tosses at once. When you think empirical, I want you to think about you have actual data that you are looking at. Some of you that have kept up with science, things like that, if you read scientific articles, a lot of times you'll hear the term empirical evidence, and that's just data-driven evidence, okay? That's what we're doing here. Empirical should tell us we're dealing with data. So for example, again, if we surveyed 100 College of Charleston students and we asked about their living situation, and we found that 39 of those 100 said they live on campus, 43 live off campus by themselves or with a roommate, and 18 of them live at home with their parents, then we can create our probability model here, okay? This is going to be an empirical probability model because we are basing on that survey of 100 students. I use 100 on purpose so the math was easy, but you basically see that 39 out of 100 here, 43 out of 100 here, and 18 out of 100 here become those probabilities. Okay. Now, on the other hand, we have something called classical probability. And classical probability is not relying on real data. We no longer have real data. Okay. Classical probability uses counting techniques and theory to say what should happen. Okay. So what should happen over the course of many, many, many trials? Just as a side note here, for the purposes of this class, we're going to say that an experiment requires equally likely outcomes. Okay. And what I mean by that is it doesn't always have to be 50-50, but if you toss a coin, you're tossing the same coin every time. Okay. So you're not tossing a fair coin, unfair coin, fair coin, fair coin, unfair coin. Like you're not rotating between those. Okay. So don't overcomplicate it. You're thinking about the same thing each time. Okay. So to calculate classical probability, we're going to look at kind of a mathy formula here, but it's really not that complicated, okay? So the mouthful explanation says if there are n possible outcomes of an experiment, and our event E has m possible ways to occur, then our probability is just the number of ways for that outcome to occur divided by the total number of possible outcomes, okay? Now, again, this probably sounds more complex than it actually is. Think about rolling your fair die and getting an even number, okay? So when we roll a die, what is our sample space? We can get 1, 2, 3, 4, 5, or 6. Okay. Now, ways to get an even. How many ways do we have to get an even? Well, we have 2, 4, or 6. So the probability of even is the 3 ways divided by the 6 total possibility ways, which is 3 out of 6, or 1/2, or 0.5, or 50%. Okay, that can be written as a fraction. Probabilities can always be a fraction, decimal, or percent. Pay attention to your homework, what it asks you for. Okay. If you wanted to talk about, if we were sitting in our classroom and took the probability that we randomly select a nursing major from this class, it would just be the number of nursing majors divided by the total number of students in our class. Okay, now notice that this is classical, this is not empirical. We did not roll a die 100 times and look at how many of them were even. Okay, we said, oh, well, this die has equally likely outcomes for all of them. And so there are 6 possible outcomes. 3 of those ways are to get an even. So 3 divided by 6 is our answer. Okay. Now we have some more complex examples that we can talk about as far as empirical and classical probability. Okay, empirical, again, is usually data driven. You're going to need actual data to find those. When you get to your course project at the end of the semester, you'll probably have a question like that. Sometimes we can use tools to make calculating our probabilities, especially our classical probabilities, a little simpler. Okay, so we can talk about rolling 2 dice. Okay, so now instead of just 1 fair die, we have 2 fair dice together, and we want to talk about their sum. We can also talk about tree diagrams. Okay, both of these are tools in the toolbox that may help you conceptualize it a little more easily. Some people are more visual than others. Some people can think more intuitively than others. So if these don't help you think about it, cool. They're just tools to keep in your toolbox. Okay. Let's talk about rolling 2 dice, and we want to observe their sums. I like to use tables to look at the sample space here. Okay. So I like to look and say, okay, well, my first die could be a 1, 2, 3, 4, 5, or 6. And my second one could be a 1, 2, 3, 4, 5, or 6. Now, if I'm concerned about their sum here, then I need to calculate the sums of all possibilities. So if I roll a 1 and a 1 together, my sum is 2. A 1 and a 2 is a 3, and so on. You're going to pick up how this happens. A 2 and a 1 is a 3, a 2 and a 2 is a 4, and so on. And I can fill out my whole table just like this. Okay, so it may look confusing right now, but how does this help me? Well, there are lots of ways this helps us. When I roll a fair die, those arrangements can happen in 36 different ways. Okay, we've listed all 36 here. Okay, we had 2, 3, 4, 5, 6, 7, 3, 4, 5, 6, 7, 8, and so on. Okay, so there are 36 options inside this box. Okay, so we know that we have 36 possibilities. Okay, so that is going to serve as our denominator. Okay, if I'm going to talk about the probability that the sum equals 4, then I need to talk about the number of ways to get a 4 over the total possibilities. Well, I see here that there's a 1, 2, 3 different ways to get 4s. And we already knew that there were 36 total possibilities. So my probability is 4 divided by 36. I could simplify that to be 1 out of 9, or I could make it a decimal. Either way, okay? That's how I can get that probability. Now, I want you to pause this and think for a second. What is the probability that the sum is at least 10? Well, at least 10 means 10 or more. So I know 10 counts. So does 11. And so does 12. So there were 6 ways out of the 36 total options that gave me a sum of at least 10. Now I can ask a ton of questions from this table, right? I can ask you, what's the probability of an even sum? Well, then you would need to go count all the evens. It's a half, by the way. I could ask you the probability of a sum of at least 7 or of less than 7. The tricky thing here is usually reading and answering the question that's being asked, okay? At least 10 includes 10, okay? Greater than 10 would not include 10. So always be careful with your number lines there. Now, another tool in addition to the tables is what we call tree diagrams, okay? And these are going to lend themselves in some cases more than others, and for some people more than others. But if I talk about a mother giving birth to triplets and we want to talk about the sex of all 3 babies, then I personally go to a tree diagram here, okay? So I'm going to make branches for each baby, okay? So baby A, the first baby out, can be a male or it can be a female. The second baby out, even if the first one was a male, the second one could still be male or it could be female. If the first one was a girl, we still have the second one could be male or female. Now, even if our first 2 are boys, our third one could still be male or female. If I have a male and female first, I could still have the third one be male and female. And so on. No matter what those first 2 are, I have the options of male and female for each one. Okay? So if I follow this tree along, let me change my color. If I follow this tree along, male, 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 my first possibility is male, male, male. Now, if I follow it along here, I get male, male, female. That's how I get to this leaf. Okay, I can have male, female, male, male, female, female. And now I can start on the other ones. Female, male, male, female, male, female, 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 male, and female, female, female. Okay? So I have 8 possible arrangements of these babies here. Okay? Now, I can use this if you're wondering, where in the world am I going? If I just said, hey, a mother gives birth to triplets, assuming the sexes are equally likely for each baby, what is the probability of exactly 2 males? Well, in how many of these did we get exactly 2 males? This one has 3. This one has 2. This one has 2. 1. This one has 2. 1, 1, 0. So this is going to be 3 of those arrangements out of the 8 total arrangements have exactly 2 males. Okay. Now, what if I wanted the probability of at least 2 females? Okay. Well, there I need to count at least 2. At least 2 means 2 or more. So this one has, the first one has 0. The second one has 1, 1. This one counts. That one doesn't. This one counts. This one counts. This one counts. Okay. So the probability of at least 2 females, there's 4 ways to get that out of the total 8. Okay. So these tree diagrams can help us organize our answers. Okay. So far we've talked about 2 different types of probability. We've talked about empirical probability and we've talked about classical probability. Remember that empirical probability is based on real or simulated data. Okay, so you're going to have actual data in front of you and you're basically going to be counting how many of that option occurred out of the total. Classical probability is based on theory. You're not actually tossing a coin 1,000 times and seeing how many of those were heads. You're just saying, hey, they're equally likely, so there's one way to get heads out of 2 possible outcomes, 1 out of 2. Or there's one way to get a 2 when I roll a fair die out of the 6 total options, so there's 1 out of 6. Okay. Classical probability is based on the theory. You are not actually performing anything. Very rarely will the 2 be perfectly equal. Okay. Remember, real data is ugly. Real data will not often give you a perfect answer. Okay. However, as your sampling size gets bigger and bigger and bigger, your number of trials gets bigger and bigger and bigger, you should see that proportion. You should see that empirical probability approach that true classical probability. That's nothing more than the law of large numbers. Okay. So if you're tossing, somebody gives you what they say is a fair coin and you're tossing it 10 times and it gives you a probability of 0.3, empirical probability of 0.3 for heads, not too worried. If you toss it 10,000 times and your probability is 0.3 in that empirical probability, that's not a fair coin. Okay. That can be your red flag. So remember, larger trials, larger number of trials is going to lead to a more precise empirical probability. It's going to give you a better empirical probability. And that is just a restatement of that law of large numbers. Okay. Now, the last type of probability we're going to talk about is subjective probability. So subjective probability is based on personal opinion. Now, I know what you're thinking. That's a bad idea. And sometimes it is, but sometimes it's our only chance. Okay. We've had a lot of days in the history of the earth, right? But every day is different. So just because it rained yesterday doesn't mean it's going to rain tomorrow. Or just because it's raining right now doesn't mean it's going to rain tomorrow. Each day has different atmospheric conditions, different things on the horizon, different temperatures, different this, that, and the other. So we can't just use past days to predict the next day. Instead, we rely on ideally an expert to take that past data into account, sure, but also to use their expert opinion to see what is going to happen. Okay, our textbook gives examples about, think about the Super Bowl. Okay, if you think about the Super Bowl here, two teams have played each other many times in the past. Okay, just because one team has won the majority of them in the past says very little about who's going to win this time. Okay, because think about that. It has changed over and over. You wouldn't just want to use empirical probability. You certainly wouldn't want to use just classical probability of like, well, there's two teams, one of them's going to win, so 50-50. Okay. If you have more information, you want to use an informed model. That is going to be that subjectivity. Remember that in the past, the two teams may have played a ton of times, but now there's different players, different field conditions, different coaching staff, different weather, different fan bases. I mean, there's all kinds of pieces that explain some of that story. Okay, so in some cases, subjective probability is our best bet, and the weather and meteorology are kind of a great example of that. Sportscasters also a decent example, although some of them are guessing a little less expertly than others. Okay, so that's really all that we're going to cover in 5.1, but now we need to pick up some other pieces of chapter 5. One of those pieces is called the complement. Okay, and the complement of an event is simply everything that is not in that event. Okay, we are going to denote it as that event with this superscripted C. When you see that superscripted C, you need to think complement. Okay, and the complement is helpful, especially because the complement rule tells us that the probability of an event's complement, so the probability of EC, is just 1 minus the probability of the event happening in the first place. And you can think about this intuitively too. If I tell you there are two options for a day, right? It's either going to rain or it's not going to rain. If I tell you that the probability of raining is 20%, then the probability of it not raining is going to be 80% because 1 minus 0.2 is 0.8. Okay? Because you know that if it's not that, it has to be whatever the probability is left. Let's look at our die example. Okay? We are rolling a fair die. So we know that our sample size or our sample space is 1, 2, 3, 4, 5, and 6 again. Okay. We are letting E be the event of a 1 or a 6. So E is 1 or 6. Okay. That means our complement is everything that is not a 1 or a 6. So our complement is 2, 3, 4, or 5. Okay. The probability of this event E is going to be 2 out of 6 because there are 2 ways to get it out of the 6 possible ways in the sample space. Okay. Probability of E complement is going to be 1 minus the probability of E. So 1 minus 2 6 is going to be 4 6. Okay. Now we can also think about that as there are 4 out of the 6 ways to get that. But notice that the probability of E, we can algebraically rearrange this, okay, plus the probability of its complement is going to be 1. So 2 6 plus 4 6 is 6 6, which is 1. You're going to see a question like this on your quiz. You're going to see a question like this on your test, okay? If you know the probability of an event, the probability of its complement is just 1 minus that probability. We also are going to talk about independent events. So if 2 events are independent from one another, that means that the outcome of one does not impact the occurrence of the other. Okay, so if I toss a coin twice, those 2 tosses are independent from one another. The coin does not remember, oh, I was heads last time, so I'm going to be tails this time. Okay, there's no impact to each other. Now, if the occurrence of one does impact the probability of the other, then you are going to have dependent events. Okay, so let's talk about this through some more examples. I already talked about tossing 2 coins and observing the results. Okay, so if I toss 2 coins simultaneously, they're completely independent of each other. What happens on one has no bearing on what happens on the other. Now, if I have 2 children, we in a stats situation are going to treat those as independent. Okay, just because I had a girl first does not mean I'll have a girl second. Those of you that are well versed in biology might know that there is somewhat of a tie there. They're arguably not perfectly independent, but for our purposes, anything we do in this class with children, we're going to say they're independent. Okay, just because you had a girl the first time, it's completely independent of what you have the second. Now let's talk about selecting cards from a deck. Okay, if I select 5 cards from a deck, and let's just talk about, if you're not well versed in cards, that's fine too. There's 52 cards in a standard deck. We're going to just talk about colors for a second. So 26 of them are red, 26 of them are black. It's really all you need to know at this point. Okay. Now, if I take 5 cards from a deck with replacement, and I look at the colors, that means I'm going to take a card, I'm going to see it's red, I'm going to put it back, I'm going to shuffle them, I'm going to do it again 5 times. Okay. These are independent events. Because it doesn't matter if the first one I got was red, I put it back, I reshuffled, and nothing changed. Okay. Now, if I do that without replacement, so I take 5 cards one at a time and I look at their colors, but I don't put them back. So my first card is red. Okay, so I had a 50-50 chance of that. I had 26 out of 52 was my probability of red, but I don't put it back. Now I have a situation where I have dependent events. Okay, because that first card was red and I'm not putting it back. Well, now there's 1 less red in the deck. Okay, so there's only 25 reds, no longer 26. And also, instead of 52 cards, there's only 51. So my probability is shifting. Okay, the probability of getting a red next time depends on whether I got a red the first time. And then the probability of what I get the 4th time depends on what I got the first 3 times. Okay, so if I am sampling without replacement, I often have a dependent situation. Okay. Now, when we talked about classical probability, we talked about theoretical and counting methods. There are a lot of ways to count the possible number of outcomes using what we call counting technique. Okay. We are only going to focus on 2 of the most basic ways in this class. Okay. We are going to talk about combinations and we are going to talk about permutations. Okay. In combinations, we are going to talk about selecting R items from N options without replacement when order does not matter. Okay. So combinations, we're choosing a set number from a pool and order does not matter. And we're doing it without replacement. Okay. So we're choosing those 5 cards from a deck without replacement. In permutations, we're still sampling R items from that pool of N without replacement. That doesn't change. Okay, so I'm still taking my 5 cards out without putting them back. However, now my order matters. Okay, and we'll look at some examples as we define each of them in more detail. So combinations, if you want to calculate it by hand, it has a kind of ugly formula. Okay, so R is the number that you're picking and N is the total number of options. Okay, so if we were choosing 5 cards, okay, out of the deck of 52, N would be 52 and R would be 5. Okay. Now, this exclamation point is called a factorial. Okay. So the factorial is you multiply all the way down if you've never used it, but you don't use 0. You just multiply all the way down to 1. So 5 factorial, for example, is 5 times 4 times 3 times 2 times 1, which is 120. 0 factorial is 1 by definition. Cannot be 0 because we'd end up with undefined fractions. I strongly encourage you to do this in StatCrunch. If you don't do it in StatCrunch, that's fine. You've got to use it in your calculator. All scientific calculators have factorial for an option. It just depends what type of calculator you're using as to where you'll find it. So I encourage you to Google that for your particular calculator. If you're using one of the TI calculators, it's usually hidden in the probability functions, the PRB. So like the multi-view, I think you press the PRB button. The 8384, it is in, I think it's hidden in a stat or a probability setting, similarly to the 89. If that's something that you need me to show you, if you can't find it on Google, that's fine. But also we can do all of this straight away with no mathematical formulas in StatCrunch, okay? In StatCrunch, you're going to go to data, you're going to go to compute, and you are going to compute an expression, okay? You can choose column from the list or you can type it, okay? In that once you get into the expression box, okay? And I'm going to show you that here in a second. On the other hand, we have permutations, okay? Again, we have R, we have N, we're not putting them back, so we have it without replacement, but order does matter, okay? And I think that this will make more sense when we do some examples and contrast when order does and doesn't matter, okay? Here, we're still using factorials. If you look back, we had on the bottom here, we had R factorial times N minus R factorial. In permutations, we don't have that R out here, okay? Similar, but not quite the same. Permutations are always going to have, if N and R are the same, permutation number will always be bigger because you're dividing by a smaller number, okay? In StatCrunch, you're going to the exact same place, data, compute, expression, and you're going to select, or you're going to type perm, and then your N is there and your R is there, okay? So let's talk about some examples here. If there are 7 people at a table, in how many ways can I choose 2 people to receive a free dessert? Okay, so I always like to start by listing my N and listing my R. How many people do I have total to choose from? 7. How many people am I choosing? 2. Now I need to decide if I'm using a combination or permutation. Does order matter? If you're at that table, do you care if you get free dessert first or second, or do you just care if you got free dessert? Exactly. You don't really care. There's no difference in outcome if you're chosen first or second. You're still getting your free dessert. Okay. So this is going to be a combination. So we are going to have a combination of 7 choose 2. If we want to do this in StatCrunch, we are going to come over here to StatCrunch. We are going to go to data, compute, expression. You can choose build here and get your combination, okay, where you can type 7 choose 2. Okay. Extra comma there. Apparently I didn't have to type it. So 7 choose 2. I could have also just typed this directly, column 7, comma 2. That's typically what I do now. And press compute. And it's going to tell you that if there's 7 people at a table, there are 21 different ways to give 2 of them free dessert. Okay, so that means you and I get free dessert, or you and your roommate get free dessert, or you and your mom get free dessert, or your mom and your roommate get free dessert. All of those are separate ways to give 2 people free dessert. So again, you're going to go to data, compute, expression, and you can type or you can go to build to get it. But we're going to do 7, 2 and press enter. And that's going to give us that 21. Okay. And turn the pen back on. So that was 21 ways. Okay, now there are 8 people on a committee. And how many ways can I choose a president, vice president, and secretary? So now I know the N is 8 because I'm choosing from 8. And how many am I choosing? I'm choosing a president, a VP, and a secretary. 3. Now, you serving as secretary is very different than you serving as president. So here, order does matter, because it does matter if you're chosen for which position. So now we're going to have permutation of 8, 3. Okay. And if we go back into StatCrunch here, we go the exact same place, data, compute, expression, and we are going to type permutation 8, 3. Okay, now again, you can go to build and choose it. Doesn't matter as long as you get it to here. When you get permutation of 8, choose 3. There are 336 of those ways. So that's a lot. Okay, make sure that you can get these. Now, I really want you to pause here for a moment. See if you can get these to yourself. I'm going to walk through them now. If there are 50 numbers in a hat, in how many ways can I select 5 numbers to win? This is kind of like the lottery, okay? I know that I'm choosing out of n equals 50, and I'm choosing r equals 5, okay? I'm choosing 5 out of 50 of those numbers. How many ways can I do that? In that case, order doesn't matter, okay? Think about the Powerball. It doesn't matter if they choose a 26 first or a 2 first. They're both winning numbers, okay? So order does not matter, so we are going to use the combination 50, choose 5. Okay. And if we go over to StatCrunch, we are going to see data, compute, expression. Combination 50, choose 5. It's going to be a pretty big number. It's going to be 2,118,760. Okay. So that is going to be 211,870. Hopefully I copied that right. That's a huge number. Okay. That's why winning the lottery is rare. And our last example is if there are 25 competitors, how many arrangements are possible for first, second, and third? Well, here, quite literally, order matters. You'd rather win the gold than the bronze, right? So here we have n equals 25 and r equals 3 because we're choosing 1, 2, 3. Now we're going to have permutation 25, choosing 3. And if we go into StatCrunch here, 25, choose 3. 25, permute 3. And press compute. We are going to see that there are 13,800 ways. Okay. That's a lot of ways for 25 people to place. Okay, make sure that you can go through these. The great thing about recorded lectures is you can rewind and go back through all that you need to. If you have any questions, you know how to reach me. And thanks for tuning in, and I hope to see you next time.